Okay, this says phosphine decomposes to produce P4, phosphorus in gas phase and hydrogen in gas phase. What would be the change in volume when 100 ml of phosphine is completely decomposed according to the given equation? Brilliant. Equation is also given. Pretty simple to balance even otherwise. But yeah, point is we can use what you call as our Gay-Lussac's law of combining volumes, right? So here what you can see is that the balanced equation is given to us. 4pH3 is going to give us 1p4 and 6H2, right? So V volume, rather 4V volume would have given me V volume of this and 6V volume of this, right? So 4V volume would give me 7V volume. So how much is 100 ml going to give me is the question, right? So 4V would have given me 7V, right? Basically 40 ml would have given me 70 ml, or 4 ml would have given me 7 ml, and so on, right? So how much is 100 going to give me is the question. Simple what you call as unitary method, cross multiply, I'll get question mark is equal to 4V. Oh no, wait. Question mark into 4V was 7V into 100. So 7V into 100 divided by 4V, VV cancels. So 700 by 4, or 7 into 25. 7 into 25 is how much? 140 plus 35. So 175, of course. 175. Right. So this is the final volume that is there, right? So this would normally have been one of the options also, just so that people make mistake. So what would be the change in volume is the question. Interesting, right? So we can see that the change will be how much? 175 is the final volume, 100 was original, so 75 is the answer. Normally I would have expected that the first option would be 175, so that you get tricked into clicking it by mistake, right? Anyway, so 75 is our answer, which is C option. Okay, this is again a simple question based on ionic mobility, based on hydration topic, right? So question is, predict the correct order of mobility of Be2 plus Mg2 plus strontium 2 plus and Ca2 plus ions in aqueous medium, right? So the idea is that as far as mobility is concerned, you will study more about this when you go into electrochemistry in 12th standard. But again, the idea is that mobility will depend upon the, obviously, as the name itself suggests, the ability to move around, right? So obviously it will be inversely related to the size of the ion, right? So mobility, obviously a smaller ion would be faster, right? So mobility is inversely related to size, right? Now the important tricky thing here is that as far as size is concerned, we are not directly looking at these ions. These are all in aqueous medium, because which means that we are looking at Be2 plus aqueous, Mg2 plus aqueous, and so on, right? Now as far as these ions are concerned, these are hydrated ions, which means that each of these Be2 plus, for example, would be surrounded by water like this. I'm taking water as a spherical thing. It's not, obviously. The negative end is the oxygen end, which will be closer to the positive cation, and the positive end will be away from the cation. And this is roughly something like what we are going to get, right? So this is one layer of hydration, more hydration, more hydration, more and more layers of water molecules would be surrounding these cations, right? So as far as the hydration, extent of hydration or size is concerned, size is inversely related to the, the actual final size of the hydrated ion is inversely related to the actual size of the cation, right? So smaller cation would have greater hydration, right? Extent of hydration is inversely related to size, basically. So we can say that Be2 plus would have maximum hydration. Be2 plus would actually be the most heavily giant molecule when in aqueous phase. Not molecule per se, body, let's just say, right? So particle Be2 plus aqueous would be the most heaviest and most bound by water molecules here, because it is the smallest, right? So all the things here you can understand are from your second group, right? Beryllium, magnesium, calcium, strontium, barium. These are your second group elements that are there. So Be2 plus, Mg2 plus, Ca2 plus, and Sr2 plus. These are, of course, as you are going down, size will increase. As size increases, reverse will be the size of your hydrated ions, aqueous ions, solvated ions. So obviously, smallest size that you end up seeing, smallest size would have maximum mobility, and that will be that of your strontium 2 plus here, because that is the largest original cation. Largest cation would mean that it is least hydration, least extent of solvation, and that would mean that it is the smallest actual aqueous ion. So this will be the fastest ion in solution, and Be2 plus would be the smallest, slowest rather. So mobility wise, I'm looking at Sr2 plus as the greatest. So where do I see it? I see Be2 plus here as maximum, Be2 plus again Ca2 plus Sr2. Okay, there is only one option where Sr2 plus is the one with the maximum mobility. Yeah, of course, the least will be that of Be2 plus, because actual Be2 plus aqueous will be the largest and the heaviest and the least mobile. Then you have Mg2 plus, then you have Ca2 plus, and the most mobility will be there in Sr2 plus aqueous. So of course, our correct answer is B option. Okay, interesting question here. Simple though. In figure 1, an air column of length L1 is entrapped by a column of mercury of length 8 centimeter. Awesome. In figure 2, length of a same air column at same temperature is L2, then L1 by L2 is. Right? So again, simple question here. What is happening is, the mercury column was originally lying like this. Atmospheric pressure is given to us as 76 centimeters of mercury. Originally, think about this. The air that is there, no mention of so throughout it's at the same temperature. So think about this air. When I'm taking this tube and I'm making it like this, or it's not exactly vertical, it's some angle, but yeah, okay, I don't know the exact value of theta, but yeah, let's just say that okay, it'll be in terms of theta. So point is, when I'm lifting it through some angle here, what will happen is that originally the mercury wasn't applying any pressure on this air, but as it comes here, mercury will push air down a bit, air will get compressed a bit. We can say that the pressure will increase, right? So as far as air is concerned, because temperature has not changed, whatever I'm doing is an isothermal process, and in this process I can obviously say that P1 V1 will be equal to P2 V2, right? So P1 is the original pressure that was there, P2 is the final pressure that is there. B1, what can I say about B1? Okay, let's speak about P1 V1, all of these one by one. So P1 will be equal to 76 centimeters of mercury. Obvious, right? Because originally when it is lying like this, if this was not 76, outside pressure is anyway 76, right? So we know here that the atmospheric pressure is what is there on this side, right? So if the atmospheric pressure and the gas pressure was different, the mercury column will move from its place, right? So if it is at settled distance, settled kind of a case here, it is in equilibrium here, mechanical equilibrium is there, then obviously we can say pressure on both sides would be equal. So P1 is 76 centimeters of mercury, and V1 we can say is okay, L1 was the length that was given. So L1 into A is the volume. Like length into area of cross section is going to give me the volume. Similarly, what can I say about P2? P2 will be how much? Think about this. Now, how do I find P2? I'm going to travel. The idea is that when you have like a column like this and all, right? Mercury column like this. So let's look at this point. Let me change the color. Right? So let's look at this point and let's look at this point, right? So as far as this bottom red point is concerned, of course it is inside, air column, right? So this is my air column. So the bottom red dot that is there, that pressure there is going to be the air pressure that is there, P2 basically, right? So it was called P2 here. So yeah, this is P2 basically, right? Now think about this. As far as the other red dot is concerned, it is atmospheric pressure that is there out here, right? And this distance is given as 8 centimeters, right? Now between these 2 points, I am suppose see, when you travel, I can travel from any point to any point, right? So if I'm going to travel from this red point, I can travel horizontally till here and then come down vertically like this. Why? Because horizontally, when I go from one point to another, pressure does not change, right? So when I'm going horizontally, pressure does not change, vertically pressure will change. So I am concerned only about this height, right? So this length is 8. If this is theta, we know this is 8 sine theta, and what is there below is 8 cos theta. I'm not concerned about 8 cos theta because the vertical height drop that is there through the liquid is going to be what is going to change pressure. Horizontal change doesn't, horizontally when I travel, pressure does not change, right? So as far as the pressure at the red dot below, which is P2, right? What is the pressure going to be? Pressure at the bottom red dot was atmospheric pressure, and then I have traveled down by a distance of 8 sine theta. So pressure atmosphere plus H rho g will be there. So I can write that P2 will be equal to atmospheric pressure is given as 76, yeah, 76 plus 8 sine theta, right? 76 is atmospheric pressure plus 8 sine theta is the vertical height. 76 plus 8 sine theta will be the pressure P2 that is there. So P2 is 76 plus 8 sine theta. And as far as V2 is concerned, we know that it will be L2 into A, right? So final volume here, L2 is the distance that is given of air column, length of air column. So the length into area of cross section is going to be the volume. So P1 V1 should be equal to V2 V2. So 76 into L1A should be equal to 76 plus 8 sine theta into L2. A obviously cancels. What we need is L1 by L2. So I'm taking this L2 to other side and this 76 to this side. So I'm going to get L1 by L2 is equal to 76 plus 8 sine theta divided by 76. So 1 plus 8 by 76 sine theta. Let's see. Let's look at the options. Yeah, of course, this is exactly what I'm getting also, right? So what is the simplifying? What can I write? This can be written as 1 plus 8 by 76 dividing throughout by 4. I mean numerator and denominator by 4. I'm going to get 2 by 19 sine theta. Right? So 1 plus 2 by 19 sine theta is what I'm looking for, which is of course there in our B option. So our correct answer is of course B option. Okay, simple question again. It says which of the following has a bond angle of 120 degree? So we are looking for something which has 120 degree bond angle. 120 is commonly seen in sp2. So if I can find the hybridization of these, I have a good chance of guessing it, right? So for finding hybridization, first thing I want to do is to calculate steric numbers. Steric number is basically number of sigma bonds plus number of lone pairs around a central atom. That will decide how many electron clouds have to be accommodated around central atom. Gives us an idea about the shape and hybridization, right? So steric number here is, the formula is valence shell electrons on the central atom plus number of monovalent atoms minus charge divided by 2. This is the formula. So if I'm looking at the first one, steric number will turn out to be 7 plus 3 minus 0 divided by 2, which is equal to 5, which means 5 overall electron clouds are there. Of course, out of that 2 will be lone pair, 3 sigma bonds will be there with the 3 fluorine atoms. So this is an sp3d hybridization, and the bond angle, of course, let me see what will, of course, 2 lone pairs are there in sp3d. We have what you call as trigonal bipyramidal, right? So tbp with 2 lone pairs, so we are going to get something like this, right? So 1 lone pair, and then 1 fluorine axial, 1 more fluorine axial, and fluorine at the center. So this is your T-shaped ClF3. Of course, no 120 degree will be there. So this is not our answer. NCl3. NCl3 is going to be very much similar to our. Okay, so NCl3, let's calculate steric number. Number of valence shell electrons is 5 in nitrogen, right? S2p3 configuration, 2s2p3. Plus number of monovalent atoms is 3 divided by 2. No charge, right? So 8 by 2 is 4. So this is sp3. And sp3 with 3 sigma bonds, of course, because 3 bonds you can see. Nitrogen chlorine bonds you can see, 1 lone pair of course, and 3 sigma bonds. So you'll have something similar to that of ammonia, right? So you'll get NCl3 like this. Of course, bond angle is going to be very close to your 109.5 degree. It won't reduce a lot because chlorine atoms are large, very difficult to push them closer to each other for the lone pair. Of course, lone pair bond pair repulsion angle is there, but still chlorine atoms are large, they will repel each other, right? So there is going to be steric repulsion there as well. So yeah, anyway, so this is definitely not our answer. It's going to be somewhere close to 109.5, but it won't reach 120. For 120, it has to become planar, and that is definitely not what is happening here. BCl3 will have 3 valence shell electrons plus 3 divided by 2. 3 valence shell electrons in boron aluminum S2p1 configuration, and 3 monovalent chlorine atoms divided by 2. So 3, therefore sp2. So of course this is our correct answer, right? So we have BCl3, which is going to have a planar trigonal kind of a shape, and we will get 120-degree bond angle here, right? Regular geometry is what we have. NH3 again, of course, very much similar to your NCl3. You'll have a pyramidal kind of a structure, 107-degree, very famous as well, right? One of the most common molecules. So yeah, NH3 is also going to be sp3, and 107 is the angle there. We know it is not 120. So of course, there is one correct answer, which is C option. Okay, this is a simple question. Arrange the following in order of their increasing first ionization energies. Right. So, increasing order of first ionization energy is what we are looking at. The elements given are, as you can obviously notice from your 3D series. Right. So, scandium is the first one. Right. So, 21. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. These are your 3D series elements. So scandium is there in our question, chromium is there in our question, copper is there in our question, and zinc is there in our question. So of course, what is happening here when we are going from left to right? So you know that on going from left to right, ionization energy is supposed to increase. So this is the order that we are going to look at. I mean, again, there are no case of exception or anything that we can come across out here. So what we can say is that of course the lowest will be that of scandium, then there will be chromium, then will be copper, and then we'll have zinc, which is of course there in yeah, oh okay, in A option. So our final answer is A.